Cycling is a popular activity for all ages, but outdoor cycling can be unsafe due to accidents, pollution, and weather. To address this, we've developed a competitive virtual cycling platform offering an immersive 360 video experience with responsive playback, real-time avatar competition, and resistance feedback for realistic uphill and downhill simulation. Multiplayer functionality allows users to race against others in real time. Our tech stack enhances the virtual cycling experience using the MetaQuest 2 for immersive VR, a 5G SDR setup for high-speed communication testing, and UDP with Bluetooth Low Energy (BLE) for low-latency data transmission. The VR app is built in Unity, with a Raspberry Pi acting as the communication hub. Our competitive virtual cycling system centers around the Oculus Quest 2 VR headset, a Raspberry Pi, and the Minura Kagura Smart Bicycle Trainer. The VR headset hosts the media server, while the trainer tracks speed, distance, and power, transmitting this data via Bluetooth Low Energy (BLE) to the Raspberry Pi. Using UDP, the Raspberry Pi relays the data to a central server, which syncs real-time stats for a competitive experience. The VR headset adjusts video playback based on the rider's speed, and the smart trainer simulates terrain by providing resistance for realistic uphill or downhill feedback. Here's a demonstration of the user experience. First, create a profile before entering the game. You can either host a game or join one created by another user. Next, select your trip mode, either single or competitive. Finally, choose your trip. For this demo, we're selecting the University of Marachua trip. Let's enjoy a ride around the campus. After entering the game room, you'll need to wait for other players to join. Here, the host creates the game room, and the server awaits ready messages from everyone. Once all players are ready, the countdown begins. 3, 2, 1, let's go! With the integration of the UDP protocol, we have achieved a significant reduction in latency. The average latency now stands at 63 milliseconds, with a median latency of 58 milliseconds, marking a substantial improvement. Furthermore, packet loss has been minimized to just 0.1%, a level so low that it has no notable impact on the overall communication performance. As you can see, several forces impact the cyclist's experience. Based on these forces, we derived an equation to accurately represent the resistive feedback mechanism. After gathering and analyzing speed and power data from real cycling sessions, we determined that the optimal value for K is around 153. This value ensures that the resistive feedback feels natural and consistent at different speeds, enhancing the overall riding experience in our simulation. To enhance realism and competitiveness, we introduced player avatars into the game. Avatar placement was one of the key challenges. We started by collecting the rider's geographical location data and mapping it to a 3D coordinate system to accurately render the rider's path inside Unity. For the competitors' paths, we applied a slight offset to the main rider's path. The 360-degree video sphere, where the video plays, was aligned to follow the rider's path, while the competitors' avatars were placed along their respective offset paths. To increase engagement and make the game more dynamic, we implemented a marker collection system. This feature rewards players based on how quickly they reach specific checkpoints, adding an extra layer of excitement and motivation. We designed an intuitive and visually appealing UI, giving players the option to customize their gameplay experience. This feature enhances user engagement and makes the game more interactive and user-friendly.